Hello, good morning, everyone. Okay, so about half of you are here already. So in today's tutorial, it's a bit of a mix in a sense that half of it are things that we have done, and then some of it are things that you will be doing in the either this week or the subsequent studio. Okay, so basically we are nearing the end of the studios already, all right, which is a good thing. Okay, we are nearing the end. So from the last studio that you did, you already have a fully functioning system, okay, where you are able to use your RPi, okay, and remotely send commands to the Arduino, all right, which means that you can actually control the robot. All right, so you have the full communication layer already in terms of the Arduino and the RPi, okay, which means that I can run my SLAM or whatever mapping algorithm that I want, okay, and based on the data feed that I get, I can also concurrently control my robot. Okay, so more or less the robot is taking shape, okay, and everything is falling into place. Okay, so the last studio plus the next, I think 2 more studios that we have is a bit complex in terms of the content. All right, so though you're not expected to understand all the code, okay, so again 90% of the code is given. All right, you just need to make some slight modification just to fine tune and understand some aspects of it. Okay, so the concept is important, what you're trying to do is important. Okay, so you don't need to worry too much of understanding all the details of the code. All right, what is important from the code we have sort of highlighted in the tutorials as well. Okay, so that is what you need to sort of make sure you have a better understanding about. Okay, yeah, so let's get started. Okay, so before I start, just I think a few of you have been asking me about the entrepreneurship and startup, and I'm missing some emails as well. Okay, so I just wanted to highlight that again and share the links here. Okay, so in terms of startup, okay, the NUSY initiative is this thing called enterprise. Okay, so I'll just put it in the chat. Okay, so if you want later, you can have a look and sort of see whether any of the initiatives or the funding is applicable or sort of interests you in any way. Okay, so this is the NUSY enterprise initiative. The other one is within computing itself, we have this thing called the furnace. All right, so this is also another avenue where you can apply, all right, and submit some ideas that you have, something that you want to try. Okay, so I mean there are a lot of opportunities, and I think something good will definitely come out of it. All right, as long as you have some idea that you are committed to work on, okay, and develop, then I think there will definitely be something good that comes out. Of course, the best thing is you get funding, all right, for your idea, and then you can use that to develop your product or your idea. Okay, if the very first time you apply and you don't get funding, okay, at the very least you will get some access to resources. Okay, maybe you get office space. Okay, you will get some office sort of admin related help in some way or another. Okay, so I think if you have something that an idea you're committed to work on, okay, and you're interested, I think you should give it a try. Of course, if later on it sort of dies off and you don't pursue, okay, then that is a different matter. Okay, but I think for the initial stage, while you're interested and while you are keen, I think you should try. Okay, once you graduate, okay, and then you join the workforce or so on, then coming back to this line may take a long time. Okay, but while you are a student, I think you have a lot of opportunities to tap onto, all right, and resources to tap onto within the university space. So I would say give it a try. Okay, it can be any idea that you have. Okay, so I think I've shared with you different ideas that our past CEG students have done. Some were something like what you do as a CEG student, hardware and software integrated. Some are pure software solutions, or some could be just an app, okay, that solves some issue. All right, so anything that you have, I would say think about it. Okay, I would say one common, because I've again helped to mentor many students, and we have gone for this kind of funding pitch before. All right, and the common I would say feedback, okay, that we usually get, all right, or usually highlight is that students tend to focus more on the technical achievements of the idea or the product. Okay, so you develop something, correct, you put some hardware together, you have some software, you have an app, and everything works very nicely, and you're excited, correct, you're very excited because it works. Okay, so when you go and pitch, you go and talk about this, you talk about what you did, all right, but they're not interested in what you did. Okay, the truth is they're interested in how what you did can lead to something bigger from the business perspective. All right, so the idea that you work on, the technical achievements, all that is fine, right? But I think the bigger picture that you need to focus on if you want to get funding, you want to get support, is how do you convert this into a more or more sort of exciting business proposal that they see that there is value in supporting. Okay, so sometimes the technical achievement is very good, okay, but if the business link to that is not solid, okay, then you still stuck. Okay, you may get some limited funding and limited support, but you may not be able to push your ideas to the next stage. Okay, so just to share one idea, okay, that one of the students in the past, okay, this was something that the panel shared with me. Okay, so I think I would just want to share with you so you have an idea. So this group of students who came up with this very with this idea of automatic soap level detection in the toilet. Okay, so they said every time they go to the washroom, they want to use the soap, but it's finished, correct? And the cleaners only come around at certain specific time slots, correct? And in between, if it's finished, nobody is there to fill it up. Okay, so they wanted to come up with a way to automatically detect the level and trigger the sort of maintenance staff to come and top it up. Okay, so that was the idea, and they implemented this using very advanced. So they used vision. Okay, use camera, a very small camera fixed to the dispenser to track, and very accurately was able to show this. So they were of course very excited. That the system works. Everything goes well. But when they brought it up to the panel, it was again, the business sense didn't make sense, because from a business perspective, a cleaning company would not want to invest in all this technology just to top up a soap dispenser. Okay, so they didn't see that it was having a good business case, but they like the technology, right? And they asked the team to go back and think of some other use case for technology, right? And what they did is they looked around, and eventually they ported this technology to an industrial application. All right, that means using this same vision technology to examine PCB boards, okay, circuits, okay, to pick out any minor faults in maybe the soldering or in the circuit design or wiring or something like that. Okay, and that was a more promising solution, and that got funding. So that is what I want to highlight. So sometimes your technical achievement is very good, okay, but the business use case is not solid enough, okay, and then you don't get the funding. All right, so you need to think of the technical solution as well as the business case for it, so that when you apply, the panel is impressed, and they think that, okay, this is something that we should support because there is potential to grow. Okay, so again, okay, those who just joined a bit later, so these are just the two things that I put in the chat. Okay, give me a minute. Yeah, so the NUS one is the furnace, all right. So that is something you can try. and the other one is this thing called the NUS Enterprise. Okay, there may be others in engineering as well, which you are also eligible to apply. Okay, so you can go and explore and see whether within NUS Faculty of Engineering they have other startup grants or things like that. Okay, so let's get started with our tutorial. Okay, so the first part is on the SLAM, all right, and the way the LiDAR works and so on. Okay, so basically, what is SLAM? All right, so the whole idea is you are able to do mapping and localization. All right, that means if I put a robot, okay, anywhere within this sort of blueprint of a house, you should be able to navigate, okay, and get some rough map of where it sees some major obstacles or major items, all right, and where it sees an opening that you can go through. Okay, so that is actually very important, right? Because that is eventually how your robot is going to navigate. Okay, so your robot may be placed at some starting point here, all right, and you must be able to, based on the LiDAR reading that it gets, okay, that it reflects back, it should know that, okay, I have something here, I have something here, but I see that there is a gap here. Okay, I see there is a gap. So I need to go in that direction to explore. So when I come here to this point, again, the same thing. I make sense of what is around me, okay, and see where are the gaps. Okay, so if you look back at our challenge, okay, usually to give you some idea, okay, I mean, you can look back at the videos. Okay, I can play it again on Thursday. So usually what happens is, okay, you will place your robot will be placed somewhere, okay, okay, and at one corner, okay, and what will happen is when it navigates, okay, so this distance will be wide enough for it to explore. It's not so cramped and tight like EPP1, okay, because EPP1 you are relying on the IR sensors and so on to keep moving straight, okay, but in our case we are using LiDAR, so we have more of a roomy sort of space, so there's enough place to navigate. Okay, so what you do is what you can expect is, as you navigate, okay, there may be some gap in the wall, okay, that tells you that you need to go in this direction. Okay, so of course when you go in that direction, again, how we divide, we do not know yet, we haven't decided, but let's say maybe I do something like this. I put a gap here. All right, so there is the color detection you need to do. That means you need to find obstacles. You need to find some obstacles to go towards to detect the color. And these are relatively small obstacles. Okay, so when your robot comes to, let's say, one place and then it sees that, okay, I have two pathways, okay, then I need to know where I see this objects to do color detection. Okay, so if you're not very sure, then you have no choice. Okay, if you don't get any reading, you need to go closer until you get something. Okay, so somewhere along the way, maybe you'll get one here, okay, and maybe you get another one here, okay, or maybe they are together. I do not know. All right, so after you go towards one, you detect, okay, then you backtrack, go towards another, then you finish. So you know that, okay, I finished this entire room. I finished this entire room. I finished. So the last place is this. Okay, but of course you can say, hey, what if I decided to come here first? Okay, if you decide to come here first and you explore this whole space and then you never find the object to do color detection, then you know that this is where the end zone is. Okay, this is where the end zone is, and then you need to go back to the other space where you still haven't explored. Okay, so the fact that you need to do color detection tells you that you need to make sure you do that first, and then you can move towards the end zone. All right, so the end zone, okay, we do not know exactly yet. Okay, later on we will decide how to sort of demarcate the end zone. Okay, and the other thing is the hump. Okay, so anywhere along the way, maybe there is a hump. Okay, so maybe over here there is a panel with a hump. Okay, which means that when the robot tries to go through, okay, it may face some resistance. Okay, so this is again a very tricky thing to maneuver. Okay, why? Because you can't see what's happening. Okay, you can't see what's happening. So the only way you know that you are at a hump, okay, because the hump cannot be detected by the LiDAR. Okay, it's flat on the floor. All right, so the only way you know that you are hitting some hump is if your LiDAR is not picking up anything and you're trying to move forward, but yet on your map, you are still stuck at the same place. Okay, at the map, you're stuck at the same place. You're trying to keep moving forward or backward or whatever, but you don't see any update on your map. Okay, so that is an indication that you are stuck. Okay, that you are stuck. That means, okay, you are not able to go over the hump. Okay, if you're not able to go over the hump, okay, which is a common thing, okay, which we saw last batch, okay, students had a lot of difficulty. What you need to do is you need to backtrack a bit. You need to backtrack a bit and then go forward with a higher speed. Okay, go forward with a higher speed. Okay, so these are things that you need to plan in advance, correct? Because generally when you navigate, you are moving quite slowly. Okay, moving quite slowly because you don't want to hit the wall and you want to have a very clear LiDAR image being formed. Okay, but when you hit a hump, you may not be able to go over if you try to move slowly. Okay, so you may need to backtrack and you need to pick up the speed to sort of go over the hump. Okay, then you can stop and then go back to your normal speed. Okay, so when you design your control interface, okay, you should have some commands in place, all right, that you can affect the speed. Okay, so some in usual sort of exploration phase, it is a slow speed, but when you want to go over the hump, it is a high speed. Okay, so that is the SLAM. All right, so generally, again, how we do SLAM is we have odometry data and environment data. Odometry data is basically the data from your encoders, wheel encoder. So in our case, we're using the Hall effect sensor. Okay, the Hall effect sensor to keep track of that information, how much your wheels have rotated, and the other is the environment data, which is from the LiDAR. Okay, so the tricky part again of this is that the encoder data, the Hall effect sensor data that you get may not accurately reflect how much your robot has moved. It only reflects how much the wheels have turned. Okay, and why this is again tricky is because when you are at the hump, okay, let's say you're at the hump over here, okay, and your wheels are here, correct? They're trying to go over. So when you try to move, your wheels may have slippage. Okay, so your wheels may still turn and you get encoder readings that sort of indicate that your robot has moved, but your LiDAR data does not agree with that. Correct? LiDAR data says that your robot is still here. It never moved forward. Okay, so you need to be careful of how you interpret your wheel encoder data. Okay, especially at the hub. Generally, it's fine. Okay, generally the encoder data can give you an indication of how much you have moved. All right, so within the robot, okay, based on how much encoder pulses you get, you can stop the motor and so on. All right, but the LiDAR data will be able to more accurately tell you whether you have really moved or you are stuck and you are just, the wheel is just slipping. Okay. Okay, so in the SLAM algorithm, all right, one of the things that you want to do is this thing called the landmark extraction. Okay, so the main idea is to process data points to extract landmark. Okay, so what exactly is a landmark? So a landmark means that when I am extracting the data, I get a lot of points, but then suddenly there's a jump. Okay, there is some significant jump from one place to another place, which tells me that, okay, this and this, there is a difference. I mean, it's not a same object, there's a different object or a different landmark. Okay, so in this Excel file, basically what you're supposed to do is you're supposed to just put a formula, all right, to sort of look at the distance based on the values that you get. All right, so this 2D distance is again from the current point together with the previous point. Okay, and they ask you to do it based on values where the where it's greater than 1 to 8. Okay, why? Because if you get any value that's smaller than 128, we say that it is treated as noise, okay, or error. Okay, so that is the first activity that you're supposed to do. Okay, so over here, basically what you do is you're supposed to take any calculate the difference using a formula. Okay, so this is just basically a Pythagoras theorem. All right, you take the distance between any 2 points. All right, but you only do it if greater than 128. Okay, and generally, if you do this, you'll be able to see that those points where the difference is large, okay, generally you will see that there is a difference in the space. Okay, it could be a bigger space or a smaller space, but you will see that generally there's a difference. Okay, and that is basically how you can detect that, okay, there is a distinct distance between this place and this place. Okay, if I'm standing here. Okay, because there's a sudden change in the values that I get. All right, so that is the spike extraction. So in the other algorithm that actually I talked about last week is this idea of is this thing called a RANSAC. Okay, so I already showed this last week, the demo. Okay, so in this RANSAC algorithm, basically what it does, it looks at a particular section and tries to get the best fit possible. Okay, now let's maybe I will show that demo again. Give me a minute. Let me open up that demo first. Yeah, so this is basically a sample set of points, correct? And basically what the RANSAC algorithm does is it will first take a random set and try to get the best fit line. Okay, so this is the first iteration. Okay, so based on the first set of sample points, it gets a best fit line. All right, and then it tries to see whether there are enough points to agree to a consensus. So if there are not enough points, it takes another sample. All right, so every time it takes a new sample, it tries to see whether the new line has more points than the current line. So if the new line that it forms has more points that agree with that line compared to the current line, then it will take the new line as the most updated line. Okay, it will discard the previous line. So in this case, you can see that the green line has more points, whereas the blue line has only 2 points. So it will discard the blue line. Then it forms another line. So in this line, you can see that it has a lot of points that fall within that consensus of how the distance between this best fit line and all the other points here. All right. So subsequently, any other line that it creates will never have enough points with the best fit line. Okay. So of course, if you have a lot of points clustered together, then you may have a few possible solutions. But in this demo, you can see that there's only one possible best fit line. All right. So subsequently, all the other iterations, okay, will try to form something. Like you can see here, it's very close. It's very close, but still the original green line is having a better fit with all the points that it has selected. Okay. So eventually, okay, it cannot find any other better line. Okay. So after the number of iterations is done, okay, you are basically saying that, okay, this is the final line rate, nothing else. So that gives you that, okay, this is the best fit line from all the LiDAR data that I got. Okay, so that is basically the RANSAC algorithm. Okay, so if you want to run this on your own, I'll just put it here in the chat. Okay, so that is basically how the LiDAR uses this RANSAC algorithm, okay, to come up with that line or the very nice map that you see. Okay, so firstly, so it has this loop where there are still unassociated LiDAR readings. That means there's still new data coming in. Okay, and the number of readings is larger than the consensus. Okay, that means you still have a lot of data. Okay, what you need, okay, to come to an agreement, and then we have not done the required number of trials. Okay, so what it does, it does set a random data selection first. Okay, so that's what we saw initially. Correct. So you have a lot of data, it just randomly selects a certain number of readings. Okay, so it could be 5, it could be 10 or whatever, and then it selects that, okay, based on some degree. Okay, because the LiDAR data is around, fully around, so it will it can decide, okay, within a certain angle I will collect all this data. Okay, and then from there calculate the best fit line. Okay, so I will take all this data and using the data I will formulate the best fit line. All right, then how many data readings lie within X centimeters of this best fit line. So once I come up with a best fit line, okay, then I will see, okay, how many readings, okay, actually lie within this best fit line. Okay, so if it is above the consensus, okay, then I do the following. I calculate the new least squares best fit line based on all the laser readings to lie on the old best fit line. All right, that means I need to make sure that I have more data points to align with this new best fit line. And then once I get a new best fit line, I can remove the lines, okay, from that do not agree from the unassociated readings. All right, so basically like what the demo does. Okay, so every time it goes through, it selects the best line, all right, based on the number of data. And if it is not able to get any other better line, then it sticks with the current line. If not, it moves on to a new line. Okay, so that is the idea behind this RANSAC algorithm. Okay, so we just want to give you the idea. Okay, so you don't need to worry about the maths behind it or exactly how it's calculated. Okay, but we just want to give you the idea of what is actually happening in the back end. All right, that you are able to extract this information. All right, and do this plot for us. All right, so that sort of just to give you some again recap of what we have done, okay, with the LiDAR and how it works. Okay, so in this part 2 was serialization. Okay, so this is where some parts we have covered, some parts we have not. Okay, so if you are still not sure after the tutorial where it is applied, how it is applied, okay, you will get a better idea after the studio. Okay, so the first thing that we're going to talk about is this thing called a magic number. All right, so what is a magic number? All right, a magic number is basically a sequence, all right, a fixed sequence that we want, all right, to use to indicate start of a data packet. All right, so it could be any number, okay, as long as the transmitter and receiver know that this is the magic sequence. All right, and we want to make sure that once the receiver receives this magic packet, it is a start. Okay, so why do we need this? Because we know that our entire data, okay, is multiple bytes. Okay, multiple bytes. All right, and after we send one packet, so we receive this packet 1, then I may immediately send the next packet, packet 2. All right, so after one packet, another packet, and so on. And at the same time, even though I'm sending one packet, all right, we know that when we say we're transmitting a packet, what we're doing, we're putting it, okay, on the serial and letting the serial hardware block transmit the data out. Okay, so of course it is not so predictable how long it will take. Sometimes the moment you put, it will transmit. Sometimes it may take slightly a bit longer, a bit shorter, and so on. Okay, so even though I may transmit a certain number of packets, it is not guaranteed that all the packets will be sent and received at one go. So sometimes there may be a short delay, okay, a short delay, and then the last packet comes in. All right, and then immediately the last byte comes in from the first packet, and immediately the next data packet comes in from the next byte. Okay, so we cannot say that it will always be one complete chunk and then the next complete chunk and so on. Okay, so it's just like when you streaming some video. All right, it doesn't mean that everything always comes in correctly. Sometimes you need to wait, the latest data is not in, you need to buffer and so on. All right, so in our code we actually handle all of that. okay, the buffering of the data, making sure the entire data packet is received, okay, before we do anything else. Okay, but the important thing is, how do I know that the incoming data is it a new data, start of a new data packet, or is it part of the previous data packet? Okay, so if there is a gap over here, okay, if there's a gap, how do I know? Okay, so this packet 1 and packet 2 is the same. Okay, that means they are both packets of data that we are transmitting. Okay, what I'm trying to show is that when I transmit packet 1, there might be a gap, a delay between some of the bytes. Okay, and then there's also another delay between the packet 1 and packet 2. All right, so when there is a delay in the transmission of the bytes, that means on the receiver side, it receives certain number of bytes, but it haven't finished. And suddenly another byte comes in. Okay, we need to know that this is part of the current packet and it's not the start of a new packet. Okay, so to do that is where the magic number comes in, to indicate that it is actually a start of a new packet. All right, so that is very important because you can expect in the real world scenario there could be a lot of data coming in through a network port. All right, okay, so of course in our case, the Arduino Uno is only expecting data from one device, okay, which is the RPi. Okay, but there could always be a lot of random bytes, okay, if there are many devices trying to talk at the same time. So how do I interpret the start of the byte stream and not think of it as some random data? So that is the magic number. Okay, so in all operating systems like Windows, Linux, everything, they have a lot of these fixed magic numbers for different type of files that they deal with. Okay, so for example, in Linux, okay, executable files start with .elf. Okay, .elf. So that is over here. Okay, so that is the indication that this is the executable file. All right, so the operating system knows that okay, this file, okay, is an executable file because the first 4 bytes have this particular magic number. Okay, similar with others. So Windows, for example, it starts with 4D, 5A. Zip file starts with PK, which is 54B, and so on. Okay, so there are magic numbers everywhere. Okay, because they are used to tell either the operating system or tell the receiver, okay, that okay, this is an indication that this is the start of this entire file or start of this data packet or something. So you know how to interpret the rest of the data that follows. Okay, so that is the concept of magic number. Okay, so this magic number, I'm not sure whether you saw it in your code yet. Okay, if you're not, okay, in the next studio, okay, when you look at the structure that is defined, okay, look at the magic number. So you'll see that that is always the beginning, the first thing that is always added to the entire data packet before anything else. All right, so now comes to another important thing, checksum. All right, so we know that we have a lot of data. Okay, so coming back here, we know we have a lot of data coming through. Okay, so previously we already saw that even with a single byte of data, corruption can happen. Okay, corruption can happen and things can go wrong. So with, of course, multiple bytes of data, give me a minute. Yeah. So yeah, so for a single byte already, we know that there is a possibility of data corruption. All right. So when we have multiple bytes of data, there is also a chance that data is corrupted once we receive it. Okay. So one way of computing or checking whether any data is corrupted is this idea of checksum. So how do I compute checksum? So imagine now I'm sending this 4 bytes of data over. Okay, so how do I use the checksum approach? So the first thing is so the whole idea of checksum is you do what we call the exclusive OR operation. Okay, so if you're not sure what is exclusive OR, it's very simple. As long as the inputs are different, the output is 1. Okay, for 2 bits. So only this and this is 1. If they are the same, they are 0. Okay, the inputs are different, the output is a 1. Input is the same, the output is a 0. Okay, so that is the exclusive OR operation. So we perform the exclusive OR operation byte by byte. So the first 0A and 1C, I do exclusive OR, then I get a first result. Okay, so this is just binary conversion, hexadecimal to binary conversion. So you just do the bit by bit exclusive OR, and then you get the first result. And then from there, you perform the exclusive OR with the next byte. So the next byte is 42. So again, I perform the exclusive OR operation. Okay, and I get one more result. And after that, I do exclusive OR with the last byte. So of course, if you have more bytes, you have 5 bytes, you have 8 bytes, you just keep doing the same thing. Okay, you keep doing exclusive OR with the next byte, and so on. And then finally, you get a result. Okay, so this result is 6E, which is the checksum. And what you must do is you must append this checksum to the data you're transmitting. Okay, so what I will do is I will need to append this data. So when I transmit, I need to append the 6E to this entire data. Okay, so what we will do is, okay, so this is the new data packet that I'm going to transmit. Okay, so of course, again, as before, the transmitter and receiver must already have agreed to all these modes of checking. Right, so we already would have configured that. Okay, this is how I'm going to compute the checksum. So the receiver is also supposed to do the same thing, and the receiver also will know that okay, the last byte that it received is actually the checksum. Okay, so when the receiver receives all the bytes, okay, you will expect that it receives 5 bytes in this case, and the last byte is actually the checksum. Okay, and the first 4 bytes are the data. Okay, so there's a question. They say why online user try to sum. Okay, so generally checksum is computed this way using exclusive OR. Okay, but again there is no right or wrong way. Some people may have chosen to implement checksum using some other technique. Okay, so this exclusive OR is more of the common way of doing it. Okay, but the whole idea of this checksum is I use my existing data and I use that to create a new data that is formulated using this data. That means this additional byte that I going to add, this additional byte must have come from the data packet. Okay, so I must have done some specific operation using my data. Okay, and then I get a data packet, which is now a checksum. Okay, so of course, it's understandable that maybe some people may try different ways of doing this. Okay, they may do OR operation, they may do AND. Okay, or they may have some other technique. Okay, maybe they say, okay, the first 2 bytes are OR, next byte are XOR, third byte are AND, whatever. Okay, but of course, the easier and more straightforward approach that is sort of used generally is the XOR, exclusive OR. Okay, that means I just exclusive OR all the bytes one by one. All right, and the basic idea is whatever I do on the transmitter side, I do the same thing on the receiver side. Okay, and then I check whether the last byte corresponds or not. Okay, so basically that is the idea. But now let's see what happens, okay, when I compute the checksum. All right, All right. So in this case, the data is transmitted this, okay, 0A1C423A, but the receiver receives this 091C413A. Okay, of course, it also received the checksum. We also receive the checksum. Now, what it will do is it will have to perform the exact operation that was done on the data packet here, okay, on the receive packet. Okay, on the receive packet. So after it performs this, let's see what happens. Huh? So the first thing that we notice is the byte that is corrupted is the first byte over here. So from 0A it became 09. So if you look at A and 9, 1010 and this is 1001. So what happens? This bit and this bit, we have two bits that are flipped. Okay, two bits that are flipped in the byte. So let's do the checksum computation. So first 09 exclusive OR with 1C. Okay, and then I get some results. Okay, and then I do the same exclusive OR again with the 4-1, and then I do one more exclusive OR with the 3A. All right, so I do all of these exclusive operations and I get the final checksum. Now, what is the checksum? The checksum is 6E. Okay, which is basically the same checksum that it received. So it will interpret that this data is correct. Okay, it will interpret that this data is correct because the checksum matches. Okay, so this sort of shows you that, again, as before, there is really always a chance that something can go wrong. All right, so the checksums, parity, whatever, they can do up to a certain level only, correct? But it cannot catch everything. Okay, so from here we can see that if there are even number of errors, okay, in a column, all right, then the data will be you cannot detect the errors. Okay, you cannot detect the errors. So again, this is a weakness. All right, and generally, okay, every algorithm that you try to detect, okay, will have some form of weakness that you may not be able to fully resolve. Okay, so that is where the receiver and the transmitter must have some form of understanding of what to do. All right, so again, the protocol between a transmitter and receiver is up to you to design. Okay, or you to decide. All right, it's just like through the network. Okay, through the network, there are a lot of different protocols. All right, where one device can talk to another device. In some cases, all right, you may have two-way communication where if you receive something in error, you can request automatically, you will request a reset of data. In some cases, if the received data has an error, the receiver just discards the data and waits for the next data and so on. All right, so everything has its pros and cons. Okay, so it's a matter of how you want to design the system and the overheads, okay, with whichever protocol that you use. All right, so that is the underlying thing. Okay, so the error can always happen. Okay, it's just a matter of whether you want to have a two-way system where you request a resend or you discard the data packet and you just wait for the next data packet. Okay, so you can make the system very simple and you say that I just transmit. All right, if the receiver detect error, means it's just supposed to not do anything. Okay, or if it hence has an error, they will try to send you back some information. Okay, so in our system, okay, that we have the RPI Arduino, you will see that if you try to send something over, all right, and let's say there's an error, it's a checksum, bad checksum, it will actually reflect back. Okay, so on your terminal, it will tell you that there's a bad checksum. Okay, so maybe something has gone wrong. Okay, again, this bad checksum, some of you may start to see it. All right, and sometimes what happens is this bad checksum happens because you are using the wrong code. Okay, so you must be very clear on which code you are using. Okay, because this serial protocol that we have started, okay, between the RPI and Arduino, you saw it, I think 2 weeks back, and then last week, and you're going to see it this week and next week as well. And each time there is a slightly different variation, something that is added. Okay, so when something is added, okay, that means the RPi and the Arduino both must match. And sometimes what happens is some groups they load the RPi with the new code, okay, which is running with new data packet format, and then the Arduino is actually having the older studio's code. Okay, and it looks the same sometimes. Okay, there's only a bit of difference here and there. Okay, so you need to be very careful, okay, to check that you are running the correct code, okay, on the RPi and the Arduino for that particular studio. Okay, and this is especially so after all the studios are done and then you're starting to build the robot. Okay, this is a common thing. You suddenly say, hey, bad checksum, bad checksum, bad checksum, because something is not right. Okay, that means the Arduino code and the RPi code, somehow there is a mismatch. Okay, so just be careful of that, okay, over the next 2 studios and once you start working on the project. Okay, so let's look at this protocol design. Okay, so again, some of this maybe you have seen it in the code. If you have not seen it yet, all right, probably you will see it on Thursday or next week. All right, so in this case, we're trying to better understand how we come up with this protocol. Okay, so of course, this protocol is, like I said, is very complex. Okay, because we're trying to send a lot of data, okay, to and fro, and we're just trying to give you this idea of how such a system can be established. Again, in reality, it always comes down to you deciding how complex or how simple you want it to be. Okay, so you can always squeeze everything together and just say, okay, I just send 1 byte. I don't want so many bytes. I just send 1 byte, and in the 1 byte, I tell Arduino what to do, and the Arduino should be able to do it. And why do I say 1 byte is more than enough? Because eventually the RPi to Arduino is only telling what? Only telling motor movement. It's only really motor movement, correct? It is not trying to send LiDAR data back or anything like that. Okay, it's only sending motor movement. So if you look at it from RPi, okay, to the Uno, if you going in this direction is the motor movement. Coming back over here is the what you call the status and sensor. Okay, so it's actually very simple data. Okay, very simple data which you can sort of encode it in a single byte. All right, but again, why we never go inside a simple approach? We want to show you how you can scale the system. All right, if you just have a single byte, then you may be thinking that it's limited. Okay, but it's not limited because you can always come up with a structure. Okay, a data packet structure like what we have shown you here, to say that I can actually group multiple bytes, as many as I want. Okay, to send a complete set of information from one device to another device. Okay, so that is basically what the T packet does. This T packet is basically the data packet. Okay, the structure, okay, that we are sending over. Okay, so basically, if you look at the code, what we do is we copy, all right, this packet information, okay, to this buffer over here. So this buffer is a character array. Okay, so whatever I have in my packet, okay, I'll just copy it over into this character array, and then I transmit. Okay, now when I try to communicate between the RPi and Uno directly, okay, I use the this approach. All right, whereas when I want to communicate over the internet, okay, which is what you're going to be doing, okay, we are going to populate an array instead of structure. Okay, so we're going to populate an array instead of a structure. Okay, where each element in the array is a character type. Okay, so why do we want to do this? Okay, why do you want to do this copying of data into an array, okay, instead of a structure? Okay, so what is the main difference? Okay, so let's look at it. So the reason why you want to do it this way is again comes back to the unreliability of exactly how many bit systems we may be dealing with. All right, So as we know, the Raspberry Pi is 32-bit system. All right, but when we transmit over the network, okay, through a PC or through some Windows or Linux-based system, most of them can be 64-bit. Okay, and at the same time, whatever device platform you use, okay, how it deals with the compiler configuration, all of these are a lot of unknown variables. All right, so for the structure approach, okay, if you remember, we did the padding. Correct. When we declare a structure, then we put a character, then we say, oh, because the RPi is 32-bit, okay, and the Uno is 8-bit, okay, so we need to do a padding. Okay, so we need to do a padding of data to make sure it's aligned to the word. All right. So this is, of course, we know. Okay, so we know, so we can sort of hack it to solve this. All right, but once you go out to the network, all right, and we are dealing with other operating systems and other devices, we can't really say how they are all configured. All right, so trying to pad the data structures correctly, okay, will be a nightmare. All right, but else, instead of trying to do a data structure approach, if I deal everything as an array of character, then it is always consistent, because an array of characters will always be an array of characters. The number of bytes will always be the same. Correct. If I declare 64 an array of character size 64, then always be 64 elements inside, and all of them will be the size character. All right, so it's always consistent. Whereas if I declare character integer, and so on, then what happens? Then everything will be mixed up. Okay, and because of the padding and all these compiler dependencies, we can't say exactly how many bytes it will occupy. All right, so that sort of unknown variable in the overall system makes it more safer, okay, to use array approach when you are communicating over the network. Okay, so okay, this 64 is not 64-bit array, it is a 64 element. That means 64 elements of character type. Okay, this 64-bit systems, okay, is about saying that how, if you try to communicate, all right, then the device that you're trying to deal with may expect a different type of padding. Correct. So in a 64-bit system, again, not knowing how the receiver end is compiled, okay, not knowing how the data, how many bytes of data are used for each data type, okay, it becomes unknown variable. Correct. So we do not know. So we need to figure out, and then we need to do the padding. Okay, just like how we did RPi with Uno. Okay, so this was Uno to RPi. Okay, so if we know that this is the exact system, there is no change, there is no unknown sort of factor, then we can do the structure approach. But since once it goes out of the network, everything is unknown, okay, using this character array approach is a safer way of doing it. Okay. Now, once you do it, of course, one of the things is even though the bytes, the size is correct, we still need to look at the Indianness of data. Okay, that means if I say that every character is stored using 4 bytes, okay, or every element in the array is 4 bytes, I still need to see whether the 4 bytes of the data follow little Indian or big Indian. Okay, so the Indianness should be correct. Okay, because if I transmit over the network and the network is going to interpret it as a different byte order, okay, or the receiving system is going to interpret a different byte order, then everything can again get jumbled up. Okay, everything can get messed up. Okay, so this byte order, again, how do we ensure that it is correct? Okay, so there are sort of libraries that we can use. that can convert, okay, host to network and network to host. All right, so these are again library functions that we can use that is provided, okay, in the system, where we can convert and make sure that the order of the bytes is matching whatever that we are going to transmit on. Okay, so what happens is, okay, for example, on the Alex side, okay, on the client side, okay, when you are trying to send data over, okay, when you're trying to send data over to the RPi, okay, you populate a buffer, okay, you populate a buffer with all the data that you want. So this is the data that you want, the first byte, the command byte, the parameter, and so on. So you have all these data packets, and you call this library function here, okay, which converts the host to network, because now you're going to transmit over the network. Okay, so when I transmit this buffer over the network, okay, it will go in the network order. All right, and once it is received, okay, over on the Alex side, I convert network to host. Okay, so I extract out byte by byte. Okay, I extract out byte by byte, but I do the network to host. So this sort of abstracts the Indianness of the system for us. Right? So we don't need to worry exactly in what order the bytes will be transmitted, whether is it least significant byte first or most significant byte first. The order will be preserved because these functions will help us to do that. Okay, so the whole idea is, okay, the array approach will work correctly because it is always going to be consistent as long as both the transmitter and receiver use the same data type of the array. So if I declare an unsigned integer 32 integer array, all right, there will always be an array of 32 integers. I mean, array of integers of size 32 bits. Okay, so it will always be consistent. So because it's always consistent and it's an array of the same data type, then there is no issue of padding. Okay, so it's a lot easier to use the array approach than the structure approach. Okay, so here they ask us to suggest. Okay, so again, these are things that you have not done yet. Okay, using the client and server, which we will be doing. Again, some of it will be on Thursday, some will be next week. All right, so the byte ordering functions, okay, like what I said, these are the ones that will convert a host to network and network to host. All right, so again, these are just to highlight the functions that we're using, okay, but we don't need to worry too much. Again, the idea is that they abstract this Indianness order for us. Okay, so whatever is the Indianness, this function will help us to convert to the correct one. Okay, so now how can I populate my structure correctly? Okay, how do I populate my array correctly in my system? Okay, so what I'm going to do is, I know this is my correct structure here. This is the data packet that I want to transmit. Okay, and what I'm going to do is, I'm going to take each of it and put it into a buffer. Okay, and this is a character buffer. Okay, since it's a character buffer, you know that a character buffer will always be consistent. Okay, depending on the on wherever I declare. Okay, so the buffer will be consistent in terms of the number of bytes I'm going to use. Okay, so how will I do it? So the first thing is, I take the first data packet and I copy it into my buffer over here. Okay, so initially my index points here. Okay, this is the index of my buffer array. So this buffer is a big array. All right, and I'm going to populate this buffer, okay, this buffer array with the data that I have. Okay, so the first thing I'm going to do is, I'm going to take the first data, okay, and convert it to the network order. Okay, because I'm going to transmit out of the network. So from host to network, and I put it in a variable. And then from there, I copy it to my buffer array. Okay, and once I copy it, then I move my index. So from here, I move here. Okay, once that is done, then I do the same thing for the next. Okay, so the next copy, which is the another data so .c. All right, and once I copy that over, then the last one, data.y. Okay, so for data.c, this is again a character, so we do not need to worry about the network byte order because it's a single byte. Okay, and once I populate this, I use the send data command. So this send data command is again something you will see in the code, okay, which is to take this entire data and transmit over the network. Okay, so this protocol basically what it does is it converts this data, okay, into a or it takes this data and populates an array, a character array. Okay, so as you can see here, we did not do any padding. Okay, we did not do any padding, okay, for the C over here. Okay, we transmit it as it is. All right, now over at the receiver side, what do I do? Okay, over at the receiver side, I do the same thing. I take the index and I point it to the first one. Okay, so of course, again, the code must be written such that it interprets it in the same order. So since I assign as X, C, and Y, all right, I also receive and interpret it as X, C, and Y. All right, so the first thing that I will do is I will take the data, okay, and interpret and extract out the first data packet with X. So X is a integer 32 type, okay, because it's an integer. All right, so I take X and I extract out first, and then I convert the byte order from network to host. Okay, and that will be the first data packet that I receive. And after that, I increment. So from index point here will increment to the next location. Okay, and in the next one, I know that it is a character because C is a character. So I just take it directly from the buffer to my variable data.c. And then again, I increment and points here. And then I take the last one, which is the data.y. And then, but because it is a multi-byte data, is integer, I again do the conversion of host to network. Okay, so basically what we're trying to show you is this approach, okay, helps to simplify and make it less dependent on us worrying about the byte order and at the same time the compiler configurations on how many bytes are needed and doing any padding and so on. Okay, because we take it as a character array that we transmit and a character array that we receive. Okay, so even though it's an array, it's a character array, okay, how many bytes relate to what data we know, correct? So technically, when we receive the data, it's all in bytes, correct? It's all in bytes. But we know that the first 4 bytes is interpreted as the first integer. Then there's one more byte that is interpreted as just a character byte. And then there's another 4 bytes that is another integer. So we know how to interpret the data. Okay, so we don't need to worry about any padding because everything is treated as a character array. Alright, so that is the advantage of using this approach compared to the structure approach. Okay, so again, it helps us to do this abstraction a lot more easily. All right, and there are of course a lot of libraries available. Okay, depending on what programming language they use and so on. So there are things like protobuf and mavlink that are available. Okay, where you can actually specify the structure. Okay, and once you provide the data and you specify this is the structure that I want, it can automatically produce the code, okay, to do this serializing and deserializing for you. Okay, so there are some very good libraries out there that you can use, you know, if you are ever going to do something like this. Okay, so that actually wraps up the whole tutorial. Okay, it's actually a short one, all right, because there was not much stuff covered. Okay, yeah, so that's why I didn't give a break as well. Okay, so I just thought we can run it through and finish it. Okay, so yeah, like I said, the second half on the serializing and all this is are things that you will see in this week's and next week's studio. Again, like I said, the common mistake that you will most likely encounter is you mix and match different code base, okay, and then things don't work. Okay, so you need to be very, very careful of managing your code correctly over the next few studios. Okay, make sure that if I'm using this Thursday's code, then RPi and Arduino both have the same code base from that studio. Okay, if not, if you try to use last week's code on for this week, okay, because you think the last week you did some work, I just want to copy over directly, then everything will get messed up. Okay, so just be careful of that. All right. So over the next two studios, basically what you're going to do is you're going to be working on this, which is the controlling RPi over the network. Okay, and then the last part is on the security, network security. Okay, so you already wrapping up everything. Okay, so for the robot wise, again, the important thing I would say is try to make full use of the time in the lab. Okay, to develop all the hardware, test everything, and make sure everything is working. Okay, it will get very stressful, okay, as the weeks go by. Okay, when especially if things don't fall in place, okay, or things start to not work as expected. Okay, so the earlier you put everything together in terms of the hardware, I think the better it is for you to focus more on just the integration of the RPi and all the other code. Okay, so in terms of controlling the robot, okay, just one thing to share. If you look at the past videos and all, the students, most of them have used the command line interface, okay, which is basically what is given to you. All right, but in the past, the students have been quite adventurous. They integrated the RPi, not the RPi, they sort of brought in their own Xbox controller. Okay, integrated that into the interface. Okay, so they use the Xbox controller to control the robot. Okay, so there are things that you can try if you want. All right, so of course the command line interface is easy and straightforward. Okay, because you just need to make sure your robot is moving and you're able to get the color sensor data correctly. Okay, other than that, I think anything else that you want to experiment, you can try, you can discuss with me. Okay, but again, remember there is no budget. Okay, you're not supposed to buy anything or use anything that is not given. Okay, even the color sensor we will issue to you. Okay, so you're not allowed to change anything or use your own components. Again, this is to ensure that everybody has the same hardware. Okay, when you're being assessed. All right. So yeah, I think that's all we have for today. So those of you who still have anything that you want to ask, you can feel free to put in the chat. You can ask me and we can discuss. If not, I will see you all on Thursday, okay, in the lab.
Prof, can I ask if there are any disadvantages of using a character array versus the old serializing way?
There's no particular disadvantage. I think it is actually more of an advantage because you don't need to worry about the padding anymore, which means that you don't really have to worry about how many bytes are used for any data type. Yeah, so there's no particular disadvantage there.
Okay, thanks, Prof.
Okay, so I think no other questions. Thank you. Bye.